Welcome to lesson 4 of 4 in this tutorial, covering resistors. This is the final video in our series of 4 lessons on the topic of current, voltage and resistance. Here are the key learning objectives for this session. First, we'll be looking at the different types of resistors and Ohm's law. We'll then look at some components of circuits and finally cover the measurements of current and PD in a circuit. Here are the AQA specification points we'll be covering in the first part of today's lesson. Feel free to pause the video now and have a quick read through them before we begin. Our first objective is to look at resistors. In the previous tutorial, we introduced the concept of resistance. We learnt that resistance in the circuit will slow down the current or the flow of charge. For any given voltage, a higher resistance is going to lead to a lower current. Resistance is measured in ohms. Resistors can also be actual components inside a circuit. Wires, lamps, motors, and other components all have some elements of resistance. Resistance, as we've just mentioned, will be measured in ohms. We can measure resistance of a single component by looking at the current that flows through it in amps and the voltage applied across its ends in volts. The higher the resistance, the lower the current for any given voltage. There are 2 different types of resistors, which are both able to slow down the current in a circuit. These are fixed and variable resistors. Fixed resistors have a constant value. Therefore, the resistance provided by a fixed resistor is constant. Variable resistors do not have a fixed value. They can change their value as the current changes. Now, we will look at the resistance of components in a circuit. In a circuit, components such as lamps will act as variable resistors. They are variable because their resistance will change depending on the current that flows through them. Exam questions will often ask you to explain the difference between a fixed and a variable resistor, so make sure you know these key points. Now let's move on to our next learning objective. We'll be looking at the current through an ohmic conductor. Ohm's law is a special relationship between the current and the potential difference of a component. As we can see here, Ohm's law gives us this characteristic straight line graph. In simple terms, Ohm's law says that if a resistance is constant, then the value of the current will depend on the potential difference. We can measure current using the following equation. Potential difference is equal to the current multiplied by the resistance. Here is the short form of the equation that is acceptable to use in AQA exams. Here are the units for this equation. They should all be pretty familiar to you. For Ohm's law to hold true, there needs to be a constant temperature, because changes in temperature can lead to changes in the resistance. This would mean that we would no longer have a constant resistance. Our fourth specification point is to look at graphs of circuit elements and their properties. An ohmic conductor is one that obeys Ohm's law. It is made by a linear circuit which makes a straight line graph. This will obey Ohm's law. This is a straight line graph through the origin. Therefore, the current is directly proportional to the voltage, assuming a constant temperature and resistance. Exam questions often use the term ohmic conductor. It's important you can understand and use this term in your answers well. Now, we will look at the resistance of filament lamps. There are 4 types of variable resistors in circuits: a filament lamp, a diode, thymistors, and LDRs. A filament lamp has a filament inside it. It's represented by this symbol here. As the filament temperature increases, the resistance of the filament lamp will also increase. This is a graph for a filament lamp, which has values in both the top right and bottom left quadrants. It is formed by a non-linear circuit, which doesn't make a straight line current voltage graph, as shown here. It produces a curved line instead. Exam questions often ask how the current through a filament lamp will vary with resistance. To answer this question, make sure you can interpret the graph in this section. Let's look at our final specification point for this part of the lesson: the current through a diode. Diodes are special since they only allow current to flow through them in one direction. The reason behind this is to do with resistance. The current always flows through the path of least resistance, so it will always take the very low resistance pathway. Therefore, the current will only ever flow through the diode in one direction. Here, we can see the current voltage graph for a diode. The graph shows that increasing the voltage one way will lead to a rise in the current after a certain voltage, as shown by this point. However, increasing the voltage the other way does not lead to a rise in current. The diode has only worked one way. Now, let's look at the graph for a diode, which is also produced by a nonlinear circuit. It is not a straight line. Instead, it produces a curved line. You should learn the 3 graphs for ohmic conductors, diodes, and filament lamps. You could be asked to draw or interpret any of these in the exam. Make sure to learn the 2 different symbols for diode and light-emitting diodes. You could be asked to match the correct symbols in an exam. We covered these symbols in one of our previous videos. We've now covered all the specification points for this section of the video. Feel free to pause now and skip back to any of the sections you are unsure about. We'll now move on to the second part of our lesson. Here is another set of AQA specification points we'll be covering. Feel free to pause the video now and read through them before we carry on. First, we will look at the resistance of a thermistor. A thermistor is a special type of resistor. This resistor depends on the temperature of the surroundings. As we can see here, the higher the temperature, the lower the resistance, and vice versa. Now let's cover the applications of these thermistors. There are several applications of thermistors. We'll cover 2 in this section. When a thermistor is placed inside a thermostat, it can sense the temperature of the surroundings. It will form part of the circuit and will enable the efficient temperature control of our homes. A fuse is used to break a circuit when it becomes too dangerous. Therefore, it can prevent an accident. Instead of using a fuse, we could use a thermistor. If too much electricity flows in the circuit and the thermistor will heat up. This increases the resistance of the thermistor, which decreases the flow of current and therefore prevents the circuit from becoming too dangerous. When given data about current and voltage in a question, you should be able to work out the resistance. Our next specification point is to look at the resistance of an LDR. Light-dependent resistors are often called LDRs. Similar to how a thermistor depends on temperature, an LDR will depend on light. Again, we will look at some applications of these in circuits. There are several applications of LDRs, including detectors and streetlights. LDRs can be used in burglar detectors. When light falls on the sensor, the resistance will increase. This allows a signal or a security alert to be triggered. In this way, LDRs can be used as part of a security system. They can also be used in automatic streetlights. They work by using the light in the surroundings to switch on and off the streetlights appropriately. Students sometimes get confused with resistors. For example, if light decreases the resistance of resistors, how can the circuit turn the street lamps off during sunrise? Well, circuits are often connected. During sunrise, the resistance may decrease in the first circuit, therefore leading to more current, which can turn off the second circuit, in turn switching off the street lamps. This is just an example to show that resistors can work in dual ways based on function. Exam questions may ask you to draw the graph of how light intensity affects the resistance of an LDR. Now, we'll be looking at how we can use circuits to measure the resistance of components. We can make two measurements in the circuit. These are current and voltage. Current is measured with an ammeter. As we learnt before, to measure current in a circuit, we have to use these ammeters. This gives us a value for the current in amps. The ammeter must be connected in series. In a series circuit, the current through every component will be the same or constant. By connecting the ammeter in series, we can gain accurate values for the current through any of the components in the circuit. Voltage is measured using a voltmeter. This gives us a value for the potential difference in volts. The voltmeter must always be connected in parallel with the component, as shown here. In a parallel circuit, the potential difference through every component will be the same. By connecting the voltmeter in parallel, we can gain an accurate value for the potential difference across the voltmeter. We will look more closely at series and parallel circuits in the next section. Our next specification point looks at drawing circuit diagrams with correct symbols. The ammeter here is connected in series with the component and the voltmeter is connected in parallel. You may be asked how current and PD are measured in circuits. It's important to remember how the ammeter and voltmeter are connected in series and parallel respectively. Finally, we'll cover one of the practical activities for this topic. We can investigate the IV characteristics of three different circuit elements: a filament lamp, a diode, and a resistor at constant temperature. First, we'll look at the experimental setup before analysing the graphs we get for each element. The graphs we'll do in this section are the same that we covered earlier in this video. First, we need to set up our circuit with the appropriate components. We need to make sure that we attach the voltmeter in parallel across the filament lamp. In this experiment, it's important that we ensure that the temperature stays constant. Now we can alter the current in the circuit by moving the variable resistor. This changes the resistance, altering the current flow through the filament lamp. we can now record the values from the ammeter and the voltmeter in a results table. Then, we have to repeat step 3 twice. Now that we've taken our repeat readings, we can repeat the steps for different resistances. We need to reverse the wires connecting the cell in our next step. This is to make the current flow in the opposite direction. Finally, we can plot a graph of our results. The current will be on the y-axis and the potential difference on the x-axis. Here's a summary of all the steps in the experiment. It's a good idea to make a note of this, as you might be asked to write these out in an exam. For a filament lamp, the graph should look like this one. It has negative values for current and PD because we switched the wires to reverse the direction of current flow. Now we can see the graph for a diode. The graph shows that increasing the voltage one way leads to a rise in current. However, increasing the voltage the other way does not lead to a rise in current. Ohm's law is the special relationship between current and potential difference of a component. It gives us the characteristic straight line graph we saw in the last experiment. This experiment is extremely popular in AQA exams. You may be asked to describe it in relation to a filament lamp, a diode, a resistor, or all three. We've now covered all the learning objectives for this lesson. There were quite a few, so if there's anything you're unsure about, feel free to skip back to that section of the video and re-watch it. We've now completed Lesson 4,